Let's hop right into Excel to calculate the values of the 5 most common option Greeks. That is delta, theta, vega, gamma, and rho. And as we calculate the values of each of them, we'll make some interpretations and learn a few things about each of them. Let's start off by defining some of our inputs. So we are going to be using the Black Scholes option pricing model to price out all of these Greeks. And we're going to be making 4 assumptions about the input to the stock underlying these option contracts. And we can see all of these assumptions right here. So we're going to be assuming that this stock's underlying price, S, right now is $40. So if I wanted to go out into the market and buy this stock, I'd pay 40 bucks. The time to expiration on all of these option contracts is going to be denoted as T, and we're going to use the value of 0.5, which means that in half a year, so 0.5 of a year, these options will expire. The risk-free rate is called R. We're going to assume it to be about 2%. So you could think of this as, let's say, the yield on a 10-year treasury, for example. And the volatility will denote with this sigma symbol is going to be assumed to be 30%. Now, one thing we can do to make our lives easier is to give all of these names so that we can reference these cells more intuitively in our formulas. So all you'll need to do, and I've already done this, is I'll just right click, hit define name. Now this one of $40 is cell D5 right here. I would just call that S and then select OK. But I've already done this for all 4 of these, so I'm going to cancel it. So I gave all these specific names. So this one is T that I'm currently selected. The next one is going to be R underscore, and then we also have one called sigma there. Now let's hop into calculating D1. The 5 key inputs you need to know in order to calculate call option and put option prices using the Black Scholes option pricing model are the 4 that we just listed. And then the 5th one is the strike price denoted as K. Now, the way that we're going to be calculating all these Greeks is we're going to be changing the strike price for the options, and then we'll see how do all of these Greeks values change. So you can see that since the underlying is 40, I started at a strike price of 20, and then I'm going all the way down to a strike price of 60 so that we can see how these Greeks behave on equal ends of either in the money or out of the money for each of these options. Now, let's hop over to D1. So D1 is kind of a complicated formula. You can see that D1 is going to be equal to the natural logarithm of S divided by K, so the underlying price divided by the strike price, which I've got here. So S divided by B14, which is K, plus the risk-free rate, plus the variance, which is just this volatility squared, divided by 2 multiplied by T. So this right here, this component of the expression is our numerator, and then we divide that entire expression by the volatility multiplied by the square root of T. So if we take T to the exponent of 0.5, that's just the square root of T. And so we can enter that and just shoot the formula all the way down with a double click. And then that will give us the D1 value for every single strike price. And what you'll see is that it's hard to interpret exactly what D1 is, but we'll interpret it as we go on to the deltas. So let's calculate our call option delta. Now this is easy. Call delta is just ND1. So ND1, we can use this inbuilt Excel formula, norm.dist. And so we're just going to reference C1, and then so the value X is just our D1 value. The mean is 0, the standard deviation is 1, and for cumulative, we're going to say true. So this is just assuming a standard normal distribution. A standard normal distribution always assumes a mean of 0 and a standard deviation of 1. Now let's just make a little bit of sense of what all these call option or these call deltas mean. So as D1 increases, you're going to see that call delta also increase. As we go down and D1 approaches 0, we should see call delta be around 50%. And we expect that our D1 should be around 0 and our call delta should be around 50% when the strike price is close to the underlying price. Now, there's a few things that can impact this, but normally you would expect these values right here to be around 0 and 50%. And as we decrease, this call delta just keeps getting closer and closer to 0. So let's hop into the sketchbook to interpret this. So I'm going to call this distribution of D1s, and we're going to assume a standard normal bell curve. And basically, these are all the possible different values that D1 could take, and we're assuming that the mean would be equal to 0. So if we just pick out a random example, see that we look at a strike price of 25. That gives us a D1 of 2.37. So let's say I drew this out here at 2.37 is our D1 value here. Then we're going to say that about, in this distribution, we can assume that about 99.11% of the possible D1 values fall below this D1 right here. So if I just sort of draw this in, we're going to say that 99.11% of the possible values fall in this shaded blue area, and that basically 8.9% would fall in this area. Now, what we can interpret that as is that at a strike price of $25, there's about a 99.11% chance that this option, this call option, expires in the money as implied by the Black Scholes option pricing model. Let's calculate put delta, and then we can interpret both call delta and put delta. Put delta is really easy. It is just call delta minus 1. So I can just take the value of each of these call deltas, subtract 1, and then I can just drag this formula all the way to the bottom. And so let's talk about what this means. So the delta of an option tells you how much is the price of the option expected to move for a 1% change in the underlying stock's price. So, for example, if we just look at this option with a strike price of 20 for a call, if the underlying price moves from 40 to 41, we expect the price of the call option underlying the stock with the strike of 20 to increase by 99.97 cents. We don't expect it to increase the full $1, but nearly. And so let's just take a look at a very interesting graph. So if I scroll all the way down to the bottom, we'll see this. So the blue line represents call delta. The orange line represents put delta. I have marked with this dashed green line our underlying stock's price at $40. You'll see that for the call delta, the options with the lowest strike prices have the deltas that are closest to 1. And then as the strike prices increase and we get closer to 40, once it crosses over that the current stock's underlying price of 40, we expect that to be near 0.5, the delta to be near 0.5. And then as these strike prices increase and the option gets more and more out of the money, we see this option delta decrease and decrease and decrease. And why is this? Because let's say we have an option delta with an option of 20, it's a strike price of $20, and the current stock price is $40. It is almost a near certainty, or almost a 100% probability, that this stock's call option that we purchased is going to expire in the money. There is a huge margin by which the stock's price could fall, and we would still be able to execute this call option. So we expect to be able to exercise it with almost 100% certainty. That means that we should experience the gain in price at nearly a 100% rate as this underlying stock's price changes. However, if we own this call option with a strike price of $60, We are so far out of the money that it is extremely low probability that this option would ever be exercised and we would gain money on it. So our option price will barely change as the price of the underlying stock changes because it's so unprobable or not probable that we would ever experience the benefit of exercising the option. So the price is barely going to change with changes in the stock price. Now, the put delta operates the same way. It is just the opposite. So when you think of a put, you gain money when the price of the underlying stock falls, right? Your put should increase in value. So with the put, if I own a put that has a strike price of $60, that means if the current stock's price, underlying stock price is $40, that means I can sell something for $60 that's only worth $40. I'm up $20. So I'm actually in the money when my strike price is above the underlying stock price. So I'm near a -1 value. So put deltas will always be a negative value, whereas call option deltas will always be a positive value. And then if I have a put option with a exercise at a strike price of 60, it is almost a near 100% certainty that this option is going to expire in the money. So I experience nearly 100% of the price changes as this underlying stock price changes. And now it is the exact opposite. Whereas if I own a put with an exercise price of $20 and the stock's price is $40, it's extremely unlikely that I'll ever be able to exercise this option to gain any value. And so my delta is near zero, and I barely experience any change in the price of my option as changes in the underlying stock's price change. Now let's calculate gamma and interpret gamma. So just right off the bat, gamma measures the rate of change of the option's delta. There is no difference between a gamma for a put option or a call option. It is the exact same. So we can calculate gamma using this formula right here. This is the Greek symbol for gamma. And the numerator of the formula is the derivative of nd1. So if you think about when we were calculating the call delta, we used nd1. This is just going to be the first derivative of that. And we can calculate that using this inbuilt Excel formula, norm.s.dist. And then for the z value, we use d1. And then for this cumulative, we put false. And we're going to divide it by the underlying stock price times the volatility multiplied by the square root of t. And so we can hit enter and shoot that all the way down to the bottom. And now let's interpret what this means. So if we go down and look at this graph, remember gamma measures the rate of change of the delta. And so let's look at that. So we can see right here that when the option is closest, the strike price is closest to the actual underlying stock price of $40, this green line, gamma is the highest. So for far out of the money or far in the money, calls and put options, the gamma is actually extremely low and it is highest in the money. We can also see that reflected in this option delta graph. So when this call option is far in the money, this line, this blue line barely changes. But as we get more closer to as the stock price is closer to the strike price, this rate of change of this line changes quite a bit. But then as we move farther and farther in the money, this line starts to flatten out. So that rate of change gets closer and closer to zero. And we see similar results on the put end of this. And so the option gamma is just a representation of that. We are going to need to use the value of D2 to calculate the theta for call options and put options. So real quick, I'm just going to show the formula for D2 is equal to D1 minus the volatility times the square root of time. And you can see that I calculated that right here. So we took D1 minus volatility times square root of time, and then I just shot that formula all the way down for all of the various strike prices. Theta is often referred to as the time decay of options. It represents the rate of decline in an option's value due to the passage of time. As time passes, we're losing potential for our option to expire deeper in the money, and hence our option will lose value as the time approaches the maturity of the option. Theta gives us an estimate of the dollar amount that an option's price would decrease each day, assuming there are no changes in the underlying asset's price or volatility. With all that being said, let's calculate the value of theta for a call option and for a put option. Now, this is the most convoluted formula for all of the Greeks. We can see the formula to calculate call option theta here, and the value of the formula to calculate put option theta here. I'm not going to spend the time to go through this whole formula because it's quite convoluted. If you want, you can freeze your screen here if you're following along and follow how I set up this formula just like this. That's the call option theta formula, and right here is the put option theta formula. Also, this file is available for purchase, so if you'd like to buy this file, you can check the link in the description or the link in the pinned comment. So, we've calculated all our call option and put option theta values. Now let's interpret them. So we've got all these values. I'm going to go down here. So I've plotted all of the option thetas. We can see on our x-axis is the strike prices, and on the left axis is the theta values. And so again, the green line represents our underlying stock price at or near $40. And we can see that theta is most significant when the option is near the money. So when the option is near the money, it represents the greatest, it represents that the probability that our option is losing time to potentially expire in the money is the greatest when our strike price is near the underlying stock price. And then as we get further out of the money or further in the money, now we see that value of the time decay is far less significant. And you can also see that option theta on both calls and puts is almost always a negative value, but there are cases when it can be a positive value, such as we see down here when this put is deep in the money, the theta is actually a positive value. And I wouldn't, you can see it's above that 0 right here, and I would interpret that as it's increasing our probability as time passes and we're very far in the money. We actually want this option to expire if it's European so that we can make sure that we guarantee our profits. You know, if the option is not expiring, then there's a probability that that stock's price could rise and we would make less money. So maybe we want to see time pass if our put option's deep in the money. Vega measures the sensitivity of an option's price to changes in the volatility of the underlying asset. More specifically, it represents the change of an option's price for a 1% change in implied volatility, all else being equal. Vega is always going to be positive for both calls and puts, so let's go ahead and calculate it and then interpret it. Let's calculate the option Vega using this formula right here. So Vega is going to be equal to the underlying stock price multiplied by the square root of T multiplied by the first derivative of ND1. And we can calculate the first derivative of ND1 using norm.s.dist, and then we'll put the D1 value in there for Z. And then whether or not it's a cumulative distribution, we'll say false. And then we can just shoot that formula all the way down for all the various strike prices. And now we can interpret Vega once we've calculated all of that. And one thing you'll notice is that Vega, option Vega, looks very similar to option Gamma. So these graphs are nearly identical. And so we're plotting all of the strike prices, and then we're plotting our Vega values on that y-axis. You'll see I put the green line for the underlying stock price at $40, and you'll see option Vega is highest when the options are at the money. at the money. As you get further and further away from the underlying stock price with your strike prices, Vega gets near zero in these tails. Now, why is that? Well, it is the same reason. It's the same thing as what we saw with option gamma. So when the stock is, or when the option is at the money, there is the greatest level of uncertainty as to whether or not the stock will expire in the money. There's a lot of uncertainty here. It could go either way. When we're out in these tails, we pretty much are almost certain of whether or not it's going to expire in or out of the money. However, at this right near the stock price, there's so much uncertainty. If we increase the volatility of the underlying stock, it greatly increases our probability that we could expire further into the money. And so option Vega is key for traders that trade based on volatility. Rho is a measure of an option's sensitivity to interest rate changes. Specifically, it represents the change in the option's price for a 1 percentage point change in the risk-free interest rate. Now, Rho is often considered to be the least important of the Greeks to option traders. Let's dive into how to calculate it and how we can interpret what Rho means and why it would matter to a trader. Let's calculate call Rho and put Rho, and I'm just going to show you real quick these formulas. So here is the formula for the call Rho. It's going to match this box right here. So it's equal to the strike price multiplied by the time to maturity multiplied by e to the negative RT. So in Excel for e, we can use this exp function, which just assumes that we're discounting this strike price by the continuous compounding of interest, and then we multiply it by ND2, which you can see represented right here, and we're going to put true for cumulative. And then for the put Rho, it is very similar. We're multiplying by the negative strike price times T multiplied by e to the negative RT. So once again, e is that exp function in Excel, which assumes continuous compounding of interest. And we're now multiplying by the negative D2. So make sure to make that D2 value negative and also put true. And then we can just shoot these formulas all the way down. Now let's go and graph and interpret the results. So here's the first thing we're going to notice in our option Rho graph is that for the blue line, the calls, you can see the Rho value of 0 is right here, right? So the Rho values are on the y-axis, the x values, the x-axis is the strike prices. So the first thing you'll notice is that the call option Rhos are generally positive, and the put option Rhos are generally negative. Now, why would that be? It has everything to do with interest rates and the cost of carry. So I've brought in the Black Scholes Model formulas of how to calculate the call option price and the put option price. And so one thing you'll notice is that the call option is going to have this thing where you take the underlying stock price and then you subtract it by the strike price. But the strike price is discounted by the discounted back to the present value. So this e to the negative RT is just a present value calculation based on the risk-free rate and the time to maturity. So you'll notice that the call option price will actually be higher if we have a higher risk-free rate. That's because we're subtracting by this discounted strike price, which and then so if we increase the interest rate, that R value, then that means the amount that we're going to subtract by is actually going to be discounted more, which means that we're subtracting a lower amount. So call price is higher if the interest rate is higher, whereas the put option is the opposite. So over here, our value is based on this discounted strike price, and it is on the left side of that subtraction sign. So it's sort of the opposite of the call value. So for put options, our put option value is going to be higher if the interest rate is lower. And that is why the option Rho is positive for calls and negative for puts. The second thing I want to point out here is that the Rho value for both calls and puts is generally higher when the option is deeper in the money and generally closer to 0 when the option is further out of the money. So let's talk about what that means for the call. So when the call is deeper in the money, right? So I can sell something for $40. For $20, I am deeper in the money. And as my strike price moves higher and higher, I get closer to the money. And then once I've crossed over out of the money, my strike price, or sorry, my row value gets closer and closer to this 0 line right here. And the put is going to operate similarly. So my row value is a higher negative number the more in the money I am, right? I can sell something for $60 that's really only worth $40. So I'm deep in the money. And then as I move closer and closer to the money, my row value becomes less and less negative. And eventually when I get deep out of the money, my row value approaches 0. Thank you for watching this video. Please feel free to like, comment, and subscribe. And if you'd like to buy the file in the video, like I said earlier, it is available for purchase. So check the link in the comment or the link in the description to purchase this file. Thank you so much for watching and have a great day.